So Advait will continue today from where he left off, talking about annealing and geosum. Right?
Yes. Okay, thanks. So last time we talked about hardness. Basically that if you want to, I see. So basically that if you want to do, you can reformulate the posterior sampling problem as a sampling from a distribution, and that getting a KL guarantee to that distribution is hard. This is where we left off last time. Okay. So there was actually a formal hardness result that we kind of briefly discussed, but also we talked about a couple of algorithms. So split Gibbs, and the reason I have this picture up is just to remind you what that was. It was this alternating projections thing where we projected onto the onto the space of images and then projected onto something that's likely under the measurements and kept going. So the problem with this algorithm was that we didn't know how many iterations it would take, even at a specific noise level. And then we did have to bring that noise level down to get the actual posterior. And again, how to do that, like reducing the noise level, that also was not clear. So we don't know how to get this guarantee. There was also the other algorithm, which was the Monte Carlo estimator, this one. So over here, we had the issue was that we don't really know how many samples it will take for each of these expected values to converge. And you kind of need that convergence to get error estimates. And so these, you can maybe try to solve these problems with some kind of distributional assumption. I think the simplest, so over here, at least with the Monte Carlo estimator, we had this expression at the bottom, right? This KL distance between the prior and the posterior that maybe can help us control this. Again, I don't know how to say anything more than that. For the split Gibbs sampling, I think there's some work that says that if the prior satisfies an LSI or is log concave, I think you can get some kind of guarantee there. But besides putting some kind of distributional assumptions or like really looking at these distributions per instance, I don't think there's a way to. I haven't been able to figure out a way to get like any kind of guarantee here. So we're going to try to reduce how strict our result is going to be and hope to get a result in that way. So I'm going to talk about a paper at the end, which is kind of a positive result on posterior sampling. Before that, we're going to talk about two relatively unrelated papers, and I don't know how to motivate them other than to say that they will be useful. They're not really related. Right. All right, so these are not related to posterior. The first two things we're going to talk about are not related to posterior. They're not explicitly about posterior sampling. They're just sampling papers. And then we'll talk about posterior sampling after that. So the first is what you asked about, this annealed Langevin dynamics. We're going to talk about it right now, actually, already. Here, annealing, I don't know if you all have been talking about annealed scores with the OU process, right? So you convolve it with a Gaussian, you get a noise distribution, and then you look at the scores of this noise distribution. Sometimes these are called annealed scores. Here I mean annealing in a more general setting. If you know about like simulated annealing from like the optimization algorithm, which was something about a temperature, it's just a more broad class of what I mean by what annealing means is just.
So just we have defined two types of annealing. We said that annealing if can either be the drift term, which is the Gaussian annealing, or the diffusion term, which is called the temperature annealing.
Right. Now we're going to talk about like something that's more general than both of them. Just in general, if you change, so we'll talk about something. It's just I just wanted to say that this annealed. When I say annealed, I don't mean the score annealing. I'll talk about what I mean exactly, but it doesn't mean like the annealed scores in the way that you all have been talking about them in DDPM. It's a more general thing. So this is how I think to motivate this. This is Langevin dynamics. I've got a pi, the distribution that you want to sample from, and then you run this algorithm. We talked about this extensively. You get some guarantee in terms of an LSI. Basically, one way to look at what's going on here is that there's some. You start out. This picture here is in distributions. These are all distributions here. Pi 0 is where you start out. Pi of 0 at 0, and then as you evolve your samples according to that SD, your law evolves according to some path through the space of distributions, starting from pi wherever you initialize pi of 0 to pi, and then you can characterize how fast it does that and so on. This is just vanilla Langevin dynamics. There's this fixed pi. And in general, there is this like dichotomy of you can view many of these algorithms from the sample path perspective of I have this X and I evolve it with this drift and diffusion or whatever. Sanjay talked about this. And you can also view it from the perspective of the law of the iterates themselves. And many algorithms, I think maybe not GANs, but outside of that, like many sampling algorithms generally have this iterative flavor where you evolve some samples iteratively, and then you can view those actually in terms of the path that they describe, right? And there could be many paths, right? There's no real, I don't know if there's a canonical path, but you can start with, I'm going to use gamma to refer to, okay, just a couple notes. First of all, gamma is going to refer to Gaussians throughout. And a lot of times there, I may not include normalizing factors. So if you ever see something that is not normalized, just pretend like there is a normalizing factor. So every measure is actually a probability measure. Okay. So there could be many paths, right, from this, from gamma to pi, right? There could be like the reverse OU process, right, which is like the DDPM type of path. You could also imagine like the optimal transport path, or this other path, which is I think is pretty interesting. It's actually the subject of that Annealed Langevin dynamics paper, where you start out with at t equals 0, you basically just have e to the negative x squared, right? So that's just a Gaussian. And then at t equals 1, it's e to the log pi, which is basically pi. And then you interpolate between these two distributions in this way, and try like basically that describes a path, right, through the distributions. You can try to implement that using an SDE or an ODE, temperature annealing. Right, but in general, there are these paths through distributions, and there are these drift terms. There are these drifts that allow you to implement these paths. Now, it turns out for any what is called absolutely continuous path, right, through the set of distributions, you can actually come up with an SDE that implements that. I think Sanjay has talked about this in detail, so I'm going to cover it very briefly. But the thing that you have to check is that this limit. So W2 here is the Wasserstein distance between mu and the W2 between mu and nu is this Wasserstein distance. Is the optimal quadratic coupling cost, right? The Wasserstein 2 distance. If this limit exists and is finite, then you call it a path absolutely continuous. And what this is saying is pi superscript t characterizes the path, right? T to pi superscript t is the path. You look at infinitesimally different distributions, so pi t and pi t plus delta. And if these are close in Wasserstein, if the Wasserstein distance scales in delta, then this path is called absolutely continuous. And basically what that's saying is if these two distributions are close, then you can implement them with this SDE/ODE. And those are the absolutely continuous paths. And then you have this exact correspondence between the description of sample paths, which is with this drift term, and the description of their laws with the Fokker-Planck equation, right? So this should be recap. I don't intend this to be anything new. But what I think is cool about this is that now instead of viewing the algorithm from the perspective of the SDE and ODE, you can view it from the perspective of the path through the distributions. Actually, come up with maybe your own path, right? I want to connect two distributions. I make up a path, right? And then I try to figure out how would I implement that, right, as an iterative algorithm. And then this could get you a new algorithm. Maybe gives you a framework to get some guarantees. And this is the setting of like Annealed Langevin dynamics, where here what we have is some map from t to pi t, right? So pi t is like a fixed. You design it. It's like a fixed path through the set of distributions. You start at pi 0. You end up at pi 1, let's say, right? Now, at any time, instead of running Langevin dynamics, I'm going to run this new SDE, which changes the target according to what time we're at. So if this t was not there, like if there was just one pi, then this would just be Langevin dynamics, right? But now what's happening is I actually change the target as a function of t, and that every time I'm basically kind of just doing Langevin dynamics, but towards this new target. It's a little bit I think it's a little bit difficult to talk about what we should hope for here because there's no convergence, right? You talk about convergence in line-driven dynamics, how close you are to pi. In this case, there is no pi. It's changing at all times. So you could ask maybe, how closely do you track this distribution? So here's a picture, by the way. So there's pi of 0. When I say pi with pi of 0, that's like the law of my iterates at time 0. Pi superscript 0 is actually the ground truth, like the actual path that I've specified. So I start out, let's just say, by taking a sample from pi superscript 0, and I'm at pi 0. And then pi sub t starts to move in some path, right? And I start running annealed line-driven dynamics, and then what you can ask is, how close are these to each other as you evolve, as you go? And maybe you can hope for them. I guess the intuition is that if you evolve this path slowly enough, then you can actually track this with annealed line-driven with this algorithm that I've described. And there is some sense, I think, in which if you do it too fast, then you can't really hope to do that because the ground truth, like the distribution that you're targeting itself, is moving so fast that you can't actually ever get to it. Right. So we're trying to track, the way to interpret this is we're trying to track this pi superscript t, and at any time we're at pi of t. And then you can ask, what is the KL distance between pi of t and pi superscript t? Okay, so that's basically the quantity that we're going to try to get at, like the subject of this paper, really. And this technique will be useful to us in a bit when we talk about the posterior sampling. So okay, now I changed notation to use rho. So from now on, rho is no, it's fine. Okay, rho is the algorithm. Like, okay, so imagine you have an evolution rho dot equals. So this is a Fokker-Planck equation. It's driven by drift term v sub t, and at time t it is at rho t, right? So this is just the Fokker-Planck equation. If this condition is satisfied, then okay, sorry. This is always true, right? You always have that the this right-hand side is called the metric derivative of the path, right? It is a property of the path alone. And if that is finite, then it turns out that any velocity field that implements this path has a L2 of rho t. This is the metric derivative. Like, this is the quantity. This is called the metric derivative.
Define what is the left-hand side?
The left-hand side is a norm. Like, it's just the two norm, the rho t norm of Vt. So Vt is a drift. The left-hand side is the rho t norm of Vt. The right-hand side is that limit we talked about previously, which is finite for absolutely continuous paths. And this is a theorem which says that for any Vt, this is true. And in particular, there is a Vt for which there is equality. And that Vt is basically the field that implements infinitesimal optimal transport maps between rho t and rho t plus delta as you vary t. Right? Okay. So Sanjay, you talked about Gersonov, right? Okay. So just to recap what Gersonov is, if you sample x0 from rho 1 of 0 and y0 from rho 2 of 0, so rho 1 and rho 2 are now going to change in time. According to these SDEs, then which correspond to these Fokker-Planck equations, then in general, rho 1 of t and rho 2 of t, the distance between them can be upper bounded in terms of one term, which is the difference in the drifts that you're using, and another term, which is a difference in the initializations that you used. All right, so this is Gersonov. We can use this to bound the term that we wanted now. Like so this is pi sub t, pi superscript t is the path that we were taking, and pi of t is the law of the iterate at time t. Let's say Vt is the drift that generates pi t. So Vt is this unique drift that is such that the 2 norm is equal to the limit of the Wasserstein distance. Then we have this. So this is just Fokker-Planck, right? We don't know what Vt is, but for any pi t, there is a Vt that does this, right? this and this are the same. This is that diffusion trick that shows you how to get like the reverse process and things like that, right? So it's basically I put in this Laplacian, and then I also had this term, and like this is basically the trick right here. But I think you've seen it before. So these two are equivalent to each other. And so now what you can do is start off 1x of 0 at pi of 0, which is your initialization, and start off y of 0 at pi superscript 0, which is like the ground truth, right? Evolve y just according to this annealed Langevin dynamics, right? So this is the algorithm that we are actually running, right? So at every time you're doing Langevin, but towards pi t instead of a fixed pi. And evolve the other one. So this other process is a thought experiment. It's using the ODE, which we have written as an SDE, but it's using this, right? In SDE form, it looks like you put in this grad log pi t term, but it's really the same thing. So x is not actually something you can implement because we don't, again, for whatever choice of pi superscript t we use, we don't actually know what the vt is. But you can imagine a process that uses vt plus grad log pi t, this one, right? And this is the one that we actually run. And then we try to use, and then we look at what happens when you apply Gersonov to these two, right, to calculate the difference between them. And it turns out that the difference in the drifts between these two terms, right? So here I've got vt plus grad log pi t, and here I've just got grad log pi t. The difference is just vt, right? So Gersonov, it characterizes the KL in terms of the integral of the differences in the drifts. That's just v sub s squared L2 pi s, right? So this is the term that corresponds to this term right here, right? This term. And then this is the initialization difference. So this is what would happen if you applied Gersonov to, again, two processes, one of which is actually annealed Langevin dynamics. That's y. And the other is this made-up process which uses vt to generate it, which we don't know what vt is, but we know that x satisfies the laws of x are actually pi superscript t. That's how we set it up, right? And so we get this. Now there's two terms here. The second term is just a initialization error, right? How far from pi 0 did you initialize your samples? The second one is the one that's important to us. It's called the action of the path pi s, right? So you can see this second term is entirely a function just of the path itself, right? So once I give you a pi s that I want you to follow, there's a vs that implements it, right? In that canonical way we talked about, right? The minimal vs. And then this quantity, which is the action of the path, is just a function of this path. It's a property of the path, and it's called the action. And it describes, as we saw, how far from pi t our annealed Langevin dynamics gets. There's an interesting property about this path, which is this action, which is that it actually depends on how fast you simulate the annealed Langevin dynamics. This is the question. This is what you were getting at. Like, this is where that kappa comes in. So what we had was this path, right? So we had pi 0, and then we had pi, let's say pi 1 after it, and we had this pi 1. And we decided to follow annealed Langevin towards pi t if instead at time t we only got to pi t over 2, right? So we basically just half the rate at which we were following this path, right? The action actually halves as well. So this is something we'll talk about now. Going back, the implication of this is that if you half the rate at which you're following the path, right, the KL distance that you care about will half as well, right? And this is actually it seems almost magical because the analogous quantity in split Gibbs, split Gibbs is another way to do. Actually, we'll talk about the split Gibbs later. I will get back to why this is. I think this is actually a pretty interesting thing. We'll talk about why that is later. Okay, so what we're going to talk about now is why when I scale kappa, the action changes as well, right? So the action scales in kappa. So imagine this new path, right? T to pi sub kappa of t, which is moving kappa times slower, so that pi sub kappa of t. So this is a new path, right? Pi sub kappa of t. It's just equal to pi of t over kappa. So at time t, it's only gone t over kappa, like to t over kappa instead of to t, which is what pi of t did. So this is by chain rule, we have this, right? So d dt, like the derivative of pi kappa t, is the derivative of pi t over kappa times 1 over kappa. This is just because I put in this is just an application of the chain rule. And then the Fokker-Planck equation for pi kappa t, you can put in, this follows from here. And then this is the Fokker-Planck equation for pi t over kappa. It has a v t over kappa. And basically the kappa just comes out and you get this term. It's 1 over kappa of here I've got the pi kappa t. I replaced the pi t over kappa with pi kappa t. This vt over kappa is the same. The point is, though, that the Fokker-Planck equation for pi kappa t would read the same thing, except that with the correct drift term here. And what this is saying is that the drift term for pi kappa t is vt over kappa, like 1 over kappa times vt over kappa. Because the Fokker-Planck equation for pi kappa t itself would read, so if I had this, pi kappa t equals negative grad v, let's call it v kappa t, pi kappa t, right? This is the Fokker-Planck equation for just pi kappa t, right? It has this new drift term. And this is the current Fokker-Planck equation for pi kappa t. So you see that the drift term for pi kappa t is just the drift term for pi t at time t over kappa divided by the 1 over kappa, or divided by kappa. And so basically this is what I've written out, right? V kappa t, which is the v kappa being the drift term for pi kappa, is 1 over kappa of the drift term for pi t evaluated at t over kappa. And plugging this into the definition of action, so this is the action of the original path, you actually get I don't want to go over the algebra because I don't really know how to explain it. I really just plugged in, if you just plug in this expression up here into the definition of the action for pi t, you get this pulls out. And the kappa gets pulled out. There's actually two kappa terms in here and 1 kappa term out here, and they cancel, so you get one left over. And you get this expression, which is to say, so the action of this A is the action of the original path pi t, and this A kappa is the action of the path pi kappa t.
Pi kappa p, and if the A kappa is 1 by kappa A. Because the action of A kappa is 1k, the action of the original process. That's the whole point. We're reducing the action.
Yeah. Then how did I get this? But you're right.
Might be the terminal time is wrong. I need to multiply that terminal time by kappa at the beginning. Have the paths land at the same.
Oh, yeah.
Okay, I'm not sure, but you're right. This is a mistake. It should be, so if kappa is 2, I'm doing it half as fast, then yeah.
Kappa time.
Okay, so this should say, yeah, sorry. Okay, this is true.
Integral should not be by kappa. The upper limit should be kappa time. Right? Yeah, sounds.
So you're saying this should be kappa t?
And then on the right, we'll just get A times, or kappa times A kappa. You can fix this offline.
Yeah, okay, whatever. This is correct. So if I go twice as slow, then the action is half as much. And this shows up in Girsanov and gets you half the KL. This is okay. That's it. So this is the takeaway from this, is that I can generally take any path through the set of distributions, implement Annealed Langevin dynamics. I get this kappa term, which describes how fast I'm simulating this, and as I scale that kappa term, I can actually scale the KL distance that I end up at. So that was one of them. The other paper we need to cover is talks about first order stationarity in sampling. I'm going to have to do this a little bit quicker because we're already half an hour in. Okay, so we talked about how Langevin dynamics is gradient flow for the KL functional in Wasserstein distance, right? You can basically use that understanding to get this expression for the convergence of KL so for the convergence of Langevin dynamics in KL. An analogous thing is what's something called the Poincare inequality. It's similar to the log Sobolev inequality, and it says the same thing for chi-squared distance, right? So if you have that a distribution satisfies a Poincare inequality, you get this kind of convergence. It's the same, very similar, very right. Okay. The problem with Langevin dynamics generally is that it doesn't mix. So unless your distribution satisfies an LSI, it doesn't mix very well. And satisfying an LSI is actually a pretty strict requirement. So an example of something that doesn't satisfy LSI is a mixture of two Gaussians, right? So here's like this is this purple mixture. And basically what happens is, imagine if you initialized your Langevin dynamics at this blue distribution, right? Then everything to the left of the center will immediately drift to the left. Everything to the right will immediately drift to the right. And you will get this really nice convergence actually very quickly, right? Where everything splits off and sits at these distributions. They mix, things will jump from the left mode to the right mode very slowly. But you don't really care because you wanted to sample, you just wanted to sample from this mixture of two Gaussians, and you did that. The problem is if you initialize even a little bit to the left or to the right, so for example here, right, then immediately all of the points, except for the few of the points that were on the other side of this, everything will immediately go to the left mode, and it'll take forever for any of them to go to drift from the left mode to the right mode. It will happen eventually. Langevin always does converge, but it will take a long time. So basically, this thing will happen immediately. This will take a long time. You will converge. But this is a specific notion of what is taking a long time here. The thing that takes a long time is for the point to jump from the left node to the right, to the left mode to the right mode, right? There is a sense in which you immediately get to some stability, right? In that immediately it comes to this mode and then stays there for a while. And there is actually there's a way to formally say that, right? So in other words, like the fact that these distributions very quickly get to a point where they're not changing very much is captured by this notion of a Fisher divergence. Sanjay, you've talked about Fisher divergence. Okay, so this is what the point is that the KL distance evolves according to this De Broglie identity in this way. It's like they're
just to connect back to what we did. This De Broglie idea. You can look at it. Remember the IMMSE relation. The MMSE error was the derivative of the mutual information. This is another way of writing it. And mutual information is a KL divergence. MMSE we know is up because of 3D is affine in the Fisher divergence. So this is remember we showed three equalities. This is another way. I didn't use the word De Broglie in class, but this is another way of saying the same thing.
Right. It says that the rate at which your KL distance, when you're running Langevin, the rate at which the KL distance changes is given by something called the Fisher distance, Fisher divergence, which is defined here. So with the Fisher divergence between alpha and beta is the expected value under alpha of this, like, I'm going to say the score difference. It's the grad log of alpha minus the grad log beta. So the KL distance here, just to compare, this is what KL looks like, right? So over here, instead of the difference in the logs, I have the difference in the gradients of the logs, and because those are vectors, it's a norm on that. There's a sense in which what a Fisher divergence guarantee gets you is kind of a local guarantee for KL distance. I do have the proof written out, but I don't think we're going to talk about it. This is the formal result, though, is that let's say mu, and I have this like mu conditioned on b epsilon at x0. So b epsilon is a ball of radius epsilon at x0, right? Mu1 conditioned on b epsilon of x0 is basically this is the density. It's the distribution mu1, but restricted to a ball of radius epsilon at x0 for any specific x0 that is specified here. So the expected value of like the local KL differences, right, between mu1 and mu2 for any mu1 and mu2. So I look at so mu1 and mu2 are some distributions. I take individual points x0. I look at small balls around them, and I condition mu1 and mu2 just to be restricted to those balls, and then I look at the KL distance of these restricted distributions. The expected value of those is governed by the Fisher distance. Like this is one connection between like what a KL distance does and what a Fisher divergence does. It's the Fisher divergence is being small basically says that when you may get like long-term, like global mode weights and things like that wrong, but if you look only local to any given point, you're sampling about correctly, like conditioned on being close to some specific point. On average, you're sampling correctly in KL. This is what the Fisher divergence says. But anyway, coming back to De Broglie, we can integrate both sides of that. We can integrate both sides of the KL of De Broglie to get. So now De Broglie's on a different page. De Broglie said this. Okay, so you can take the integral on both sides to get that the difference in KL at the beginning versus the end is this is just the fundamental theorem of calculus, right? Like I've replaced I've taken this integral of the derivative, so it's just the difference in the KLs. And from here to here is De Broglie, be negative, right? And now this is the integral of a bunch of Fisher divergences to pi, and it turns out that Fisher divergence is convex in the first argument, and so you can use Jensen to get this. Here, this is the Fisher divergence between this integral, right? This is where the convexity comes in, where I've replaced the integral on the outside with an integral on the inside, right? So what the right-hand side here is t times a Fisher divergence of an average distribution to my target, and on the left-hand side I have a difference in KL distances, right? And so overall, if I initialize correctly, so if KL pi 0 to pi is 0, like this is the initialization, then what this is saying is that the Fisher divergence of the average iterate, right? That's what, so pi of t at any time t is the law of the t iterate. What this is saying is that the law of the average iterate is close to pi polynomially fast, right? So I run this for time t, and my KL distance, my Fisher divergence actually goes as the KL distance of the of where I initialize down to 0 at rate 1 over t, right? So this was for the Fisher divergence towards a fixed pi, right? So, yeah.
Would you remind us which way time is running? Is pi t moving toward noise or data? Like pi or
pi of t. So there's a fixed pi. Pi of t is the iterate, the law of the tth iterate when you run Langevin. Right now there's no pi. The pi t is about to come, like pi superscript t, where I change t is about to come in. But right now pi of t is just the forward. Yeah, you're running Langevin towards pi. And this is the average. So this is a Fisher divergence between the average iterate and pi. And I'm saying that it goes down as 1 over t. Okay. So the actual reference that I have here also has a discretization analysis where they say what happens. So what I've written out is the proof for if you actually looked at the continuous process. When you discretize it, there's another error term, but I don't have time for that. The thing that we're going to change in this, though, is instead of looking at this for Langevin, we're going to need to do this for annealed Langevin, right? For reasons that, for the posterior sampling thing. And so we're going to have to modify this to work also if pi itself was changing. So now there is going to be a pi superscript t. It's going to follow, the proof is going to be very similar, but just have one more error term besides the discretization. So this is the quantity that we're now going to care about, is the rate at which the KL distance between pi of t, which is your iterate, and pi superscript t, which is now made up, like it's your path, right? Pi t is like the path that we were talking about in the annealed Langevin dynamics setting, right? It's your laws. Like you're targeting a changing distribution, and pi t is like the distribution at time t. So this derivative is now the sum of two derivatives, where I first take the derivative with respect to the first, like here I take the derivative with respect to that time variable, and here I take it with respect to this one, right? This is like there's two t's, and I'm just adding the derivatives with respect to both of them. The first one is the same as before. So this derivative is just this is just De Broglie, right? I'm fixing this t, and I'm taking the derivative with respect to like the time in the first argument, and De Broglie just gets you that this derivative is just the negative Fisher divergence. This is the same as before. The other one, we're just going to do some algebra to get this into a form that we can work with. So this is the definition of KL distance. So I have d by ds, the expected value of pi of t divided by pi s, d pi t, right? So this is, from here to here, I've just written out the definition of KL distance. From here to here, I swapped the order of the integral and derivative. We'll assume, as always, that you can always do these kinds of things. From here to here, we observed that this t, this t, is not s, right? Like with the derivative is with respect to s, t is fixed now, like the numerator, and so you only really get the thing in the denominator, and so it is like you can rewrite that as the expected value under pi of t of the derivative of pi s, of log pi s, right? So this quantity, right, just the inside, so forget the expected value, just the argument of the expected value, that is now similar to how we had an action for KL. This quantity is now just a property of pi, like the pi superscript t, like the path that I picked. So I picked a path. You look at this quantity d by ds log pi s, right? This is the derivative of the density, of the log of the density. Where this gets a little bit more complicated is that in the action was not at all a function of your algorithm, right? There was no pi of t when we defined the action. Here we have to take an expected value over pi of t, which is something that which is the law of your algorithm. So this is a little bit more complicated, but the conclusion after, when the dust settles, what you get is that a similar quantity, right? The KL distance between the average, the Fisher divergence between an average iterate and pi can be bounded in terms of the original, like the whatever initialization error, and this new quantity that is determined by how fast your path moves around. Okay, are there questions about this? I'm pretty sure I did this super fast, but here's what it is. Okay, so then we'll talk about basically this paper about like some positive result for posterior sampling, which kind of just combines these two ideas. One of them was like the annealed Langevin dynamics, where I specify a path pi t, and then I can tell you, depending on how fast you simulate it, how close you get to how close you are at all times. And then the other thing which showed that for a very similar thing, but for Fisher divergence. So instead of KL, we looked at how to modify the Fisher divergence guarantee for Langevin to a Fisher divergence guaranteed for annealed Langevin. Right? So here's how we're going to do this. In general, I want to get to this distribution. Right? This is my actual posterior, P e to the negative Ly. I can start here. Like I can always sample from a standard Gaussian. I know how to go from the standard Gaussian to my prior, right? This is what like DDPM and things like that get us. We assume we have accurate access to scores and things like this. So we can do this orange thing. We can also do the green thing. So this point here is a Gaussian times e to the negative. Oh, so this term. This distribution is a Gaussian times e to the negative Ly. So it's like a Gaussian restricted by the likelihood, right? It's the product of these two things. So this measure is actually, if you assume Ly to be convex, this is strongly log concave, right? Because the Gaussian itself was strongly log concave, and then I multiplied it by pointwise by another log concave distribution, and so this is strongly log concave. Because of that, you can sample from this distribution just using Langevin dynamics. You don't have to do anything fancy. The thing that we want to do is sample from really some kind of combination of both of these things. We want to get to this one. So the way that we're actually going to do it is to start from gamma and go to gamma e to the negative Ly using Langevin. We can do this pretty easily. And then go from gamma e to the negative Ly to p e to the negative Ly by using annealed Langevin, where at any time, so when we talk about annealed Langevin, we need to specify this path pi t, right? So what it's going to be is p t. So this is the tth annealed, like the OU pt times e to the negative Ly. So as you can see, when t is 0, this is just p e to the negative Ly, right? That's this one. When t is a very large thing, so p, let's say infinity, e to the negative Ly. So this is just the regular posterior. This is actually about gamma e to the negative Ly, right? Because p infinity is about gamma. Like it's just a Gaussian. Like when you run the OU process starting at p for a really long time, you get to a Gaussian. So p infinity e to the negative Ly is just about gamma e to the negative Ly. So this is something we can start with gamma e to the negative Ly, anneal ourselves from here to here using along this path, pt e to the negative Ly. Because of the way that notation with the time, actually we're going to do p. We're going to take a really large value of capital T, and then go p capital T minus t e to the negative Ly. So at time t equals 0, this is so pi 0 basically is close to gamma e to the negative Ly, and pi capital T is close to p e to the negative is actually equal to p e to the negative Ly. So this is the path we'll take, and if we can show that the things we talked about previously, like the action and that the other quantity that showed up in the Fisher divergence, if we can show those two things are small, then we'll actually be able to we can say how closely we can implement this path, the stage two path in going backwards. So which one?
Stage 2.
Stage 2 is annealed Langevin dynamics. So I described a path, right? This is the path, pi t, right?
Yeah.
And then now we can just run annealed Langevin dynamics for this path.
What is pi t?
This.
What is that?
Oh.
Somewhat.
But the annealed after.
This is the path. Oh, shoot. This is the path. So we're going to run annealed Langevin dynamics for this path from t equals 0 to t equals capital T. And I want to say hope for the best, but basically we'll get Annealed and Fisher divergence guarantees for this path. That's for stage 2. What is your question?
Maybe yeah. No.
Okay. So but you understand stage one. So stage one, going from gamma to gamma e to the negative Ly, is just Langevin, right? Now, once we're very close to gamma e to the negative Ly, which is about the same thing as p 500 e to the negative Ly, we'll start running the reverse, like this path, this pi path, from there to pi 0, or pi capital T, which is the posterior.
But how do you implement stage 2 path? Because I have the annealed scores only for P, not P tilted with even minus Ly.
Yeah, no, that's this, right. Right.
Is Ly known?
Yes, exactly. Yes, but I think you're asking that you don't know the.
Not annealing P, annealed version of just P.
Uh-huh.
I mean, I know the annealed version of P tilted, right? That's the whole.
No, okay, so this is not, I'm not doing p e to the negative Ly of t, like t of that. So this is different than this quantity. P e to the negative Ly t, that is the noised posterior. That we don't know. I'm replacing this with pt e to the negative Ly.
Because just if you take the log, it's just code plus some of that.
Right, so that's,
like guidance.
so okay.
The log term, just so that if people are lost.
Yeah,
It's take it, yeah, okay.
Right, so this is, okay, this calculation is, mu is the posterior. This is the notation from the paper. So grad log mu t is just this, pt of x e to the negative Ly of x. And this just breaks up. So I have the left side because I have the scores from DDPM, and I have the right side because you just assume that, you know Ly really well.
Fair enough. But like a key insight is that I can't just go from gamma directly to P in minus Ly, but I do it 2 stages. I can do both stages separately in this tracking.
You can't. So the thing is, you can't do any of this. This is not, you will not converge to the right distribution. That's what the hardness is saying. So, but this is an algorithm you can implement.
Implementing.
Yes.
I can't implement directly DDPM from gamma.
Yes.
I don't know like what you wrote, annealed of
Yeah.
P tilted.
Yeah.
But I know the 2 separate things.
Yes. So this is, in some sense, we're constrained to do this because we don't know what p e to the negative Lyt is. Right? We only have, we can use this and then try to really, I mean, one way to put what we're about to do is use this instead and see what we get. It's roughly the right thing, right? Like I'm denoising and then I'm taking a gradient step towards my likelihood, and then I just repeat this process. It's, in some sense, what you're doing is going from pt e to the negative Ly to pt minus delta e to the negative Ly, right? Is kind of like, remember in split Gibbs, at some point you could reduce the noise, like you would run split Gibbs to convergence at some noise level, and then reduce that noise level and again run it to convergence and keep doing this, right? So instead of running it to convergence every time, right, at a specific noise level, if you just did it once, both, like you did one projection onto the images, one projection onto likelihood at a specific noise level, and then moved on to the next noise level, this is kind of what this algorithm does. In fact, that you can actually make that connection pretty formal. You don't run them to convergence though. So one of the characteristics of this type of thing is that I'm never actually going to be at pt e to the negative Ly. I'll always be somewhere else. But if you go slowly enough, then you can actually track this distribution. That's the point. Right. So this is, I mean, this is the, I'll just talk about what the algorithm is now. So there's four parameters. T1 is the thing that specifies for how long you should implement stage 1. So stage 1 was just Langevin towards gamma e to the negative Ly. You should just run Langevin for some amount of time. It turns out if you run it for 1 over epsilon squared log 1 over epsilon time, you can get to within epsilon of gamma e to the negative Ly. Okay. T2 is where to start the reverse process for stage 2. So remember I said to take a t that was large enough here? So over here we started with a capital T that's large enough that capital T e to the negative Ly was about gamma e to the negative Ly. So this is what that value of t needs to be. And it turns out if when you work it out, it turns out to be about log d over epsilon, basically log 1 over epsilon is where you have to start the reverse process. Then there's this kappa, which is the speed factor from annealed Langevin dynamics. And then there's a step size eta. This is the step size for discretization, and we'll set that to be kappa to the -1/4. So the algorithm, I guess we've talked about this, but just formally, you start with x0 sampled from a standard Gaussian. For time t1, for t1 iterates, you do this. This is just Langevin dynamics for gamma e to the -Ly, and then this is I guess the main thing with the annealed Langevin is you go for now from t2 kappa over eta down to 0 now, this thing. At any time, we're running towards a slightly different drift. The time, so this is the score function, right? This approximates grad log p I delta over kappa of x, I minus 1. This is where this is where the scaling factor comes in, is that at various times, I'm using basically I delta over kappa noise level instead of what you might do without the kappa is just I delta. So a few of the assumptions that we need are that the prior is M sub Gaussian. The score needs to be Lipschitz. So this is the prior score, right? This is actually the second assumption is pretty standard. Many sampling, DDPM, for example, like the original guarantee is required as well. And the loss function, besides the fact that we know it exactly and we can take derivatives through it and things like that, it is also R smooth and convex. So something about its Hessian. So the sketch of I'll just give a sketch of this proof. Basically, what we can show is that from the analysis of annealed Langevin dynamics, we know that the KL distance between mu t minus t, which is what we're trying to track, right, and the law of the algorithm itself goes as this action, right? Which is this Vs, we don't actually know what it is, but for whatever path we have come up with, it is the velocity field that would generate it. So this one problem here is that we don't know what Vs is, but we will try to work out how to bound it later. And then we can do the same thing, so this is a KL guarantee. We can, using the Fisher divergence thing from the second part of this talk, we can say that the Fisher divergence scales like this. Like this is the expected value over the law of the algorithm of the rate at which the log density changes. Okay, the lemma that actually you can use to do both of these things just bounds this quantity, right? The derivative of the pointwise densities, right? So it turns out that there's enough regularization in the original OU process. So remember that mu t is actually comes from the OU process of p times e to the negative ly, right? There's enough regularity in pt that mu t is bounded by this term, e to the negative t 1 minus e to the negative over 1 minus e to the negative 2t times some constant. I'm going to call this a constant that is a polynomial in the sub-Gaussianity, the Lipschitzness, the smoothness of the reward, and the dimension, times a quadratic in x. So it's at most quadratic in this. So the thing about this first term is that it's for large t, it's about e to the negative t, right? So it decays very quickly. And for very small t, it's about 1 over t, right? So it's actually polynomial in t for small t, right? I'm just going to assume that all of these, you can work it out in exactly, but just for readability, we're going to assume that all of these MLR are all constants. Let's say they're even equal to 1. In the appendix, I did work it out, and it doesn't really affect anything. So here's the overall result that you get, which is some version of a compromise about from like getting a full KL guarantee, which is that, so if rho t denotes the law of xt, right? So this is the standard, like the way that we've been talking about rho t, then there exists a t star, right? Such that when you run that algorithm, the KL distance between mu t star and rho t star, which is like basically the KL distance between the ground truth and your law, goes down as poly d and 1 over kappa. And then the Fisher divergence does the same thing. This should be 1. Right? So the thing what you might have hoped for is to get a KL mu 0, rho 0 is less than something. But the hardness result means that you can't do this, right? So you can't actually get the KL distance of your algorithm to the ground truth mu 0. So instead, this is for some t star, which we can show to be poly 1 over kappa. Kappa is a thing that we can tune ourselves. So we can set kappa to be 100 or 1,000 or something like that. And the larger we set it, the smaller t star becomes, right? So for a polynomially small t, you can get KL guarantees to mu t. For a polynomially small t star, you can get KL guarantees to mu t star. And the Fisher divergence is actually to mu 0 itself, right? So this is a KL guarantee. The Fisher divergence guarantee is to mu 0, like the actual posterior. So a couple of things, I just have some notes about what the implications of this are. First of all, maybe you notice that the argument of the KL guarantee here is flipped compared to what it usually is. So in Langevin dynamics, usually you talk about the KL guarantee of your law compared to pi or the ground truth or whatever. Here it's the other way. This is actually a very annoying thing. It happens because we used Gersonov. And a lot of the Gersonov-based proofs have this, like Sitan's work, for example, the KL guarantee is, the arguments are switched as well. One way to avoid talking about that is to give a TV guarantee. So since the TV, first of all, is upper bounded by KL, this is Pinsker's inequality. And because TV is symmetric, you can just say like the TV between the two is small. Another thing is you can actually get just this guarantee, right? The Fisher divergence guarantee already from Langevin, right? We talked about how to get the Fisher divergence for Langevin dynamics. The problem is, since we're solving a posterior sampling problem, if I just gave you a Fisher divergence guarantee, that's not very useful, right? So here's an example of the kinds of problems that you could have. Imagine if P was your prior, the blue one, right? So I have 3 modes, and then the likelihood wants to select 2 of the modes, right? So your posterior should actually be the second. So the first line is describes the problem. There's a P and then e to the negative Ly. The second row is the actual posterior that you want. So it's just a selection of the second 2 modes, right? The problem is that if I just gave you a Fisher divergence guarantee, which is what just Langevin would get you, then actually you could even return this mu prime, right? Which almost completely ignores the third mode and just puts all of the weight on the second mode, right? And it turns out that
That's why sort of Fisher is sort of leads to mode collapse.
Right. So this is called mode collapse, and it's one of the things about Fisher divergence guarantees is that they have this like unsatisfying property that they're very insensitive to mode weights. And the problem is that in posterior sampling, arguably the modes with large weight are the thing that you're trying to find, right? Like if you wanted to sample conditionally from this mode, and then you gave me a guarantee that was in Fisher, I might have collapsed that mode, and then I'm solving like I'm giving you a completely vacuous guarantee. This is kind of why our annealing schedule was useful, because the point of this KL guarantee. So this was basically what I described as what is the problem if I just told you the second thing. If I just gave you the second thing, it's almost useless for a posterior sampling perspective. But what happens is, because we did this like warm start thing, like we went first to gamma e to the negative Ly, and then we slightly denoised that. We went to like pt to the negative Ly, and we reduced the t over time. it turns out that there's enough of a warm start phenomenon in that you're actually closer to like what we saw here. Oh, it was in the other. So there's enough of a warm start between PT and PT minus delta, mu t and mu t minus delta, that you can actually get like a KL guarantee to come through for some amount of time, right? So this is where the mu t star is. This is why there's a t star here instead of a 0. It's like up until mu t star, right? We actually have KL guarantees, right? Which is the thing that prevents this kind of collapse, because for mu t star in this setting would be a mixture of these two modes, and because you have a KL guarantee for that, you actually know that you do have mass on both of them, and so in combination with the Fisher divergence guarantee is the thing that gets you like the posterior sampling, some like weaker notion of a posterior sampling. Okay, so this is where like the discussion of the kappa and Annealed Langevin, I think, is useful. You could try to do exactly this with split Gibbs. The problem is I don't know how to say for a specific rate at which you reduce the noise level, how many iterations it would take you to converge, and how fast you can change that. I actually thought about this a lot. Somehow, because we ran Annealed Langevin dynamics instead, there's just a magic parameter kappa that pops out. And if I double kappa, I'm just half as close, or twice as close, right? This is, but otherwise, I think for things like if P satisfies an LSI, for example, you can actually get similar guarantees for a similar algorithm using split Gibbs.
But we don't have LSI. That's the whole point.
Right. So
you shouldn't go down those rabbit hole.
Right.
You see LSI just by virtue of, it's probably very weak, right? It gets worse as you get closer to your target, right? Like that would be the guarantee for split Gibbs, is that I've noised the prior. That noised prior has an improved LSI over the prior, because it's headed towards Gaussian, right?
Yeah.
That guarantee degenerates as you move up the prior.
Okay, so there's a couple of interesting things about this. First of all, it does get worse. So you definitely have to assume that P itself has an LSI. Because, so okay.
Yeah, it's a win all the way down. Yeah.
So okay, gamma e to the negative Ly has an LSI because it's log concave, right? P e to the negative Ly only has an LSI. Okay.
He does.
No, actually, so that's the thing. That's not even true. This is what I thought was true, and then, okay, here's why.
Actually, there's too much of a digression. We should not worry about class.
Okay, so the point is that that's not true. It turns out.
This is non-public. It says that just because P could have an LSI and P to the minus L need not, or vice versa. Here's a clean example, but I don't think that's the point of it.
No, I'm done. This is all I had to say about. I was not going to do any proofs. This is basically it. This is the approximate posterior sampling guarantee.
Okay, maybe then we can stop at this point, and then you can discuss this offline, because I think that's too much of a digression from.
Okay.
Yeah. Thanks. So Advait, thank you very much. So I want to now cycle back, and so you have seen the sort of posterior sampling loop. You have seen that you can do some sort of an approximate posterior sampling, even though it's hard. But next 3 classes are going to be complete mode change again. If you have lost track of all about posterior sampling, doesn't matter. We reset it. Okay. Next class is discrete diffusion. So I will start from scratch. I'm going to develop the mass diffusion, discrete diffusion language model. So we're going to do diffusion language models. Next class is going to be mass diffusion models with the pointer towards other models. I don't have time to do every single model. Then the class after that is most likely going to be discrete flow matching. So doing discrete diffusion models through flow mapping. And then finally, sort of some recent work from us on what we think are the state of the art discrete language models. So that's basically where it's going to be for the next few classes. Okay? So it's again a reset from whatever is going on. Okay? So we'll start from scratch and see where it goes. Thank you.